Thank you, Nico. Yeah, welcome to this talk. And in this talk, we want to demystify how Beam runs on top of Flink, or how Beam integrates with Apache Flink. And I just want to clarify something at the beginning, because this logo is, some suggested that this is kind of irritating, because Flink sits on top of Beam, but the title is Beam on Flink. So there were actually some suggestions on Twitter. Well, actually, some irritations. Wait, this sits on Beam, but that's weird. Also, there was a suggestion maybe to create a GIF of a squirrel which drives the car, because Beam has like these headlights like a car, you know. Unfortunately, I didn't get to it. I'm sorry. So we have to live with what we have now. So some words about me. I'm primarily a software engineer, and also I consult companies. I'm also PMC member of both Beam and Flink. And I used to, work for Viverica, which in these days was called Data Artisans. So I'm just telling this to you because you might be wondering, what credibility does this guy have to talk about these things? Also, I worked with Google and currently with Lyft on Beam and Flink. So my focus used to be like more Flink and Beam. Now it's more Beam and Flink. So I'm working mainly on Beam portability, which I think is a really, really exciting subject, and on the integration with the Flink Runner. So what are we going to talk about today? What are we going to learn? So this is basically divided into 4 chapters. The first one is Beam and Flink. What are they again? You might think you know what Flink is. Maybe you don't know exactly how Beam works or what Beam is. We're just going to recap and take a different perspective on how these things are different and work together. And then we're going to look at how the actual integration works. And we're going to first do this in a more simple way, and then we will take a look at Beam portability, which is a totally new use case enabler because you can use different languages. And we will also see that the runner itself, so the part of the integration, also had to change in order to support portability. So let's start right off. So what is Beam actually? Well, originally Beam came from Google. The original code, it was called the Cloud Dataflow SDK, but it became an open source project and has been developed in the open source since 2016. It is very similar to Flink in the sense that it's for parallel distributed data processing, and it sort of takes a different stance than Flink, because it's not actually a runtime. It's more like a framework to build these applications. And you have a unified API, which Flink doesn't have yet. And that has always been like a big reason for people to use Beam, because you don't have to differentiate between batch and streaming that much. And the other thing that it makes it interesting is that you can actually swap the execution engines. So you can run it with Flink, but you can also use other engines like Google Cloud Dataflow or Samza or Hazelcast Jet. I will show you the list in a second. And the really exciting part about Beam its newest addition is that you can use any programming language or any supported programming language of your choice. So how does it look like? So basically, we have a set of SDKs included with Beam for different languages. It used to be only Java. Now it's Python and Go as well, and we had Scala for a while, SQL as well. And in Beam, we have these so-called runners. And there's a runner for every execution backend. So the Flink runner translates for Flink, and then there's also the Apex runner, the Google Cloud SDK, Google Cloud Dataflow runner. And this way, we can run with multiple languages on multiple execution engines. So I think that's pretty cool. And how does this look like, just the API? From a very abstract perspective, this is not a Beam API talk. Beam has this really elegant API, I think, where you start with a pipeline. So basically, your Beam job is called a pipeline, like a Flink job, and it starts with an empty pipeline. Then you apply a transform, you get a P collection. You can then go on and on, do that, And also, you can write out data, of course, to other systems. But that's just another transform. So how does it look like? We have a pipeline object. We do like pipeline create, supply some options. Then we do a P apply on the pipeline. We get a P collection. Then again, we do apply as often as we want. Then we can set a runner, for instance, Flink Runner, and we can just run it. So it's very elegant. And actually, what are these transforms that we just apply to the P collections? So Beam has this notion of primitive and composite transforms. So the beauty of this is that we actually only have a very small set of primitive transforms that we need to support, which is like read, ParDe, GroupByKey, AssignWindows, and Flatten. And any other like transforms that we use are composite transforms, so they break down in these primitive ones when doing translation. So for example, a combine, if we want to implement a combine, we could just do like GroupByKey and ParDe. We will see the example on the next slide. But we could also implement our own combine translator, which would do something like combiner lifting so that you pre-aggregate values before you send them over the network. So just conceptually, what are the most important transforms that we have in Beam? So there's parallel do and GroupByKey, basically, which I guess is the parallel do these are the most important. Parallel do is basically, well, maybe like a Flink process function, or huh? It's not like a flat map. It's could be like a rich flat map. Basically, you're right. But it's very powerful. So here, let's just do the word count. We have like a series of strings to be or not to be, and we assign this key value object. And that's another thing about Beam. It tries to be very concise in the sense that if you use a key value object and you have set the key, like in this case to these words, then automatically, if I do a group by key, then these keys will end up on the same machine, and you get an aggregate list of all the values for each key. And then you can use another ParDe to sum up these values. So I'm not going to show any code, but conceptually this is very simple, but it's also extremely powerful because we can do much more with ParDe, which I will show in a second. So what is Flink? You probably think you know what Flink is, and it would be weird to explain Flink on a conference like this, but it's actually multidimensional, I would say, from a Beam perspective, because it's clearly an API, or actually two APIs, maybe even more if we take SQL and Python, the new Python API into account. But it's also like a processing model, right? Like Beam, actually. So it supports stream batch processing, and it's also an execution engine. So at Beam, we like to think about Flink as like a toolbox for building your own execution layer, your own API on top of the Flink runtime. Why would you use Beam on Flink? Kind of already touched this, but you have the unified API. You have a Python support or other languages, like full support with like running your custom libraries and everything. And you have also the power of Flink, of course, right? That's exactly once, the robustness, the memory management, save points, these are all supported with Beam. And if you have existing Flink infrastructure, great, you can run Beam there, but it also runs on Google Cloud Dataflow, Spark, Hazelcast, and many more. And we have some really cool features like side inputs and cross-language pipelines, which you actually you don't get it in Flink. So what do they have in common? Well, they're both a distributed data flow execution model. They support batch and streaming. They have event time, processing time notion. So that's very important because Beam has this concept of watermarks, timers, and state, which Flink actually was heavily inspired by in the early days. So both projects kind of were inspired by each other, I would say. And we also have windows and triggers. But we will actually see that just because we have this concept doesn't mean we leverage this. For example, in Beam, we don't We don't use the windows and triggers that Flink offers because they are slightly different, and so we have our own set of libraries which enable us to use windowing and triggering. This is like a gross oversimplification, but I just wanted to highlight some of the differences. So we have two APIs with Flink. Flink is very much about having control. You can configure everything. You can set the parallelism for each operation. You can do a partitioning, keying as any way you want it. Basically, specify your own partitioning function. You can do resource usage optimization, bind to some machines. You can also do key selectors and stuff. So it's a very sophisticated tool. Beam, on the other hand, likes to be like more auto-tuning. So you have less knobs. I mean, you can still configure, but some stuff, like for example, if you have a key value object, then the key is always inside a key value object. And if you want to specify a different key, well, you have to create a key value object that holds the key, and that's very explicit and sort of auto-tuning or auto-managed in that sense. Then also window assignment is pretty different in Beam. In Beam, we assign windows eagerly, so anytime we have data in our Beam pipeline, it's already windowed. If it's not part of a interval window, then it's part of the global window, actually. And Beam does sort of things lazy. It just takes the data as it is, and then later when you do a windowing, it will assign the windowing. The same goes for like key grouping. So if you want to get all the key values for a key on a task manager, you would in Flink you would do like a window operation or so, which you would then have to key the input before. In Beam, it's very explicit, so you do just a GroupBy Key, and it already expects that your input is like a key value object. Then there's some really cool features not present in Flink, like side input, which technically Flink supports, but on a very low level. So you basically have to manage your inputs. If you read from two streams, you have to kind of manage them yourself. And the two have actually two different type systems. Flink has its own type system, Beam has its type system, and its own coder's way to serialize, deserialize data. So that's something to take into account. If we look at the Flink Runner, it actually comes, as a user, you don't need to worry about this, but this is a more technical talk, so I thought I mentioned this. It comes actually in 4 flavors. So we have a classic runner, which exists for batch and streaming, because they have 2 different APIs in Flink. And then there's the portable runner, also for batch and streaming, because again, we have 2 APIs in Flink. So that makes actually internally 4 translators, 4 sub-translators for the actual Flink runner. And the classical is a good question. Classical way is just running Java pipelines, whereas in the portable way, we can also run Java pipelines, but additionally we have Python, Go, and other SDKs that we can use. So basically, if you use the Flink runner, you are in the classic mode in Java. If you use the portable runner, then this will still, I will show you in a second, you use the Flink runner, but this is actually a portable way to submit any language then to the Flink cluster. So let's start off with the classic Flink runner. So in theory, it's quite simple, right? We just take our Beam pipeline, which is like a graph, and we have our translators, ParDe for GroupBy Key, for AssignWindows, and Flatten, and we just generate basically the API calls as we read the graph, read them from the sources, and then we have our Flink job, right? So the way this works is actually, because I mentioned coders, coders are the Beam serializers and deserializers. So the way this works actually, from a very simple perspective, is just as we see the coders in our Beam pipeline, we generate coder type information, which is Flink's way of specifying the type of something. And when we then want to retrieve the serializer, create serializer, Flink would do it during runtime, then we return also coder type serializer, which is again a wrapper around, it's a Flink construct, but it contains the Beam coder. So that way we can just use Beam's coders and support the native serialization that they offer. So I want to go over this like in this sequence to explain you all the primitive transforms that the classic Flink Runner offers. So the next one would be read, which is a way to read data into your pipeline in Beam, and we basically support this by also two wrappers, one for batch, the source input format, and one for streaming called the unbounded source wrapper. And we support all the primitive that Beam offers, but on Flink. So that's like splitting the source, emitting watermarks, and emitting elements, of course, from the source. And also we have some special adapters because the unbounded sources are used in streaming, they can't be used in batch, right? So we have also a way to, in a streaming pipeline, to read bounded data, because that's a different interface. So we have this fancy bounded to unbounded source adapter, which really proves also how great names you can create when you use Java. So let's go to the ParDe. That's I think more interesting. ParDe has a lot of features like site inputs, site outputs, state and timers. It is basically translated by the Flink Runner using in batch the Flink doFn function or the Flink stateful doFn function, and in streaming we have the really powerful doFn operator. In streaming, the operator takes care of checkpointing and buffering of data during checkpoints, and also, of course, watermark emission, state, and timers. And the way this works is that Beam has this interface called the doFn runner. And so we don't have to implement all the logic to run a Beam ParDe ourselves. We have actually bundled runners, which are implement this interface called the simple runner or the stateful doFn runner. And it pretty much handles all the logic for us, like retrieving state, executing timers, setting timers, and we can add our own wrapper around this, but mostly we just use these Beam interfaces, or these Beam provided classes like the simple runner. So site inputs are a kind of special thing, and they have to also be handled in that doFn operator. So basically how it works is you have a main input and you have the site input data. And the issue is that you kind of have to, because site input means that you will actually materialize all the data to all your parallel instances before you start processing here, because that's like, imagine you have like here in this example, like a rule, like a set of rules that you want to distribute to all the operators, parallel operators. Then you have to make sure those rules are like materialized before you actually start processing. So the doFn operator here, it has to wait to actually process the main input. And that's also realized with a special doFn runner, like I mentioned on the previous slide, and that's called a simple pushback site input doFn runner. The names get longer and longer. For batch, it's a bit simpler because in batch we have all the data already available, so we can just materialize all the data and send it to the operator. We don't have to wait until we receive all the data, right? Because they can arrive interleaved, right, and not necessarily at the same time. So then we also have side outputs in ParDe, which is like a way to multiplex the output instead of just having one output. And actually Flink, I don't know, since 1.3 or 4 has this as a native construct. So we can actually use in streaming just send it to a different output instead of the main output. And batch, we wrap every element in like a raw union value and basically assign a tag and the actual value and send this out. And then we can, if we want to select from an output on a different operator as an input, we just do a filter where we extract only the tag that we actually want. Okay, and the last thing that I want to mention for the ParDe is state and timers. So Flink has, as you know, in streaming, has a timer, a way to access user state or general managed state and timers. And Beam also has basically the same idea. So it's pretty much like implementing these interfaces, the Beam state internals and timer internals for Flink, which is called Flink state and Flink timer internals. For batch, it's a bit different, again, because we have the opportunity to read all the data for a particular key. So we can just actually process, use Beam's, process all the data and provide us with in-memory state internals and in-memory timer internals that Beam has, because in the state API, timer API does not exist for Flink, for the Flink batch API. So, and almost done here. The GroupBy Key transform, it's a way to get all the same keys, like here, the yellow ones are the same distinct keys, and they go to get all the keys to a machine to evaluate their values, like we did in the word count. And it's sort of like similar to what happens when you run a window function, for instance. And in batch, we actually use the group reduce operation, and we do a locally combine of values if we have like a combine function also, so we do avoid sending data over the network too much. And for streaming, we use Beam's reduce FN runner. Reduce FN runner is basically handling all the logic of grouping by the key and by the window. So we provide all the data. We send all the data where all the key elements which have the same key to one machine, and there the reduce FN runner runs and decides, when the window is ready to fire and when we can execute the window function. The last transform I want to talk about is assigning windows, and this is actually the simplest of all, because it's literally just a flat mat function where you have an element like hello, and everything is wrapped in a windowed value in Beam and assigned by the global window by default. So when we want to translate a window, assign windows transform, we just call the window assigner that is contained in this transform, and we emit we take the input element and emit a bunch of windows. So if we have a tumbling window, then it will only be one element usually. But if we have, for example, sliding windows, we would emit multiple values for different time spans. Yeah, and that's now the last one. Flatten is very simple because Flatten is just a way to combine multiple P collections which have the same type into one P collection, and that's, if you used Flink before, then it's just a union. So we do union and merge all these together. And of course, we would be done now here, but we chose also to translate some more composite transforms. I mentioned combine already, so this is using a group combine in a batch and a group reduce followed by each other, so we can effectively combine locally the values before we send them over the network. And for streaming, again, we use functionality provided in Beam called the system reduce FN, and it actually has a way to also do a combine already when we receive the data, so we don't end up buffering a lot of data which can already be combined in memory. The other transform that we have, composite transforms reshuffle, and we just use Flink rebalance, which evenly partitions the data among the task managers. So if we get to staging execution, how easy is it to run the Flink Runner? It's actually very simple because it's just another Flink application, right? You just need to submit your jar against the cluster, and There's the blob library cache will take care of distributing the libraries. So it's just another Flink program. This is a bit different when we get now to the portable Flink Runner. If we look again at the vision that I showed in the beginning, so I assigned some years here because I think it's interesting. Beam really started out as a Java-only project. In 2014, the Cloud Dataflow SDK was released, and very soon, even before it became an Apache project, we had Flink and Spark and the Spark Runner emerge, which, yeah, we're working already quite well with the Java SDK. But over the years, as more runners also emerged, there was the desire to have other APIs which are more accessible to people, like SQL and Python, and eventually also Go. And we just realized that we had to come up with a completely different approach to solve this problem, because we were not dealing with the JVM anymore, but we had a totally different runtime involved, like the Python runtime. So the way we solve this is if we take the original approach here, where we just do everything in Java. We have also the execution engines all in Java, which is really convenient. Well, at least the open source ones are in Java. Then it's all very simple. We have some execution bundles here. I mean, execution libraries, which I presented to you before, like the reducive N runner. So to help translate this, but it's all kind of simple and stays within the JVM. Now, when we go to the portability, suddenly we have to have additional translators to translate the SDK logic of the Java or Python SDK to the runner, which is written in a different language. And same again also for the execution. We now have like Python code in Java. What are we going to do with it? So we had to come up with a more clever way than let each runner just figure out its own solution. So we actually have a universal representation of the pipeline, which is called the runner API. And that's a protobuf definition, which they are protobuf libraries for every language, so we can actually load and use them across languages. And then also for the execution, we had to come up with a better way to handle basically an interface between the different languages to handle communication with the runner or the execution engine and some foreign language like Python, which runs in a completely different process. And that's called the fun API, because it's so much fun. And so what does that mean for our runner? Does it mean we have to rewrite everything? Well, actually, most of the logic stays the same, at least for the runner. So we have a new way to now execute our ParDes, which is called ExecutableStage, and that's basically everything that can be combined, all the transforms that can be combined and have to actually require a foreign SDK like Python. And then we still have GroupByKey. We assign Windows also in SDK, so we don't have to take care of this in the runner anymore. We still have Flatten. The one thing that changed in the course also is to replace read with this unbounded and bounded source interface with something more generic, let's say. I'm not going to go into detail, but it's basically a much more powerful way also to support advanced features like dynamic splitting, which were not supported in the old read way. And so we decided also to go with this. And SDF is actually just a ParDe which can do a few more things. So, but we again end up with 4 different translators. Again, if you want to check this out, it might be interesting for you. So how does this really work now? I mentioned that if we just have the classic way of running Java job with Beam, it's kind of very simple, the submission process. If we are on portability, which means we want to run Python or even Java, but in an external process decoupled from the Flink runtime, we have this process sort of. So we have the SDK where the user creates an application using the Beam SDK, be it, for example, here in Python. And we end up with this runner API with this universal representation of the pipeline. And then this is sent over via the job API to the job server. And the job server is actually also a Beam component, because we need a new way to stage all the dependencies that we require. Because in the old world, we would just take a Java jar and deploy this to all the hosts, and then we would be good to go. But in a new way of translating, we have the Java dependencies, because Beam has some libraries that Flink needs to have, but we also have Python or the other SDK. So it's a bit more complicated. That's why we have the job server. The job server has like an artifact stager, which basically receives the Python pipelines or any dependencies that we require, and it holds these and stages them to, for example, a file system, different ways of doing it, and then also it takes the pipeline that we submitted and submits it to the Flink cluster. And then during execution, we have these like normal translation that we've seen before, GroupBy Key and Flatten, but you also have executable stages, and this is always when we need to run a Python function, for example. We have an input, it goes through the network, or loopback if you have it, loopback network if you have it on the same machine as the task manager, and it processes with this so-called SDK Harness, which is just maybe a Python process. It's a bit of a fancy name, and it sends back the results to Flink again. And yeah, of course, to be able to start the SDK Harness, we have to stage all the libraries that the user used here. So that's taken care of also in the process of submitting a job to the job server. Yeah, so this is basically how it works. This SDK Harness, it can actually run by default in a Docker container, because that's most convenient for people. It can also run in a dedicated process that is started by a shell script, for instance. It can also be like an external worker pool, which basically creates workers as they are needed by the Beam job. And it can also run embedded for tests if you are using Java only, though, because yeah.
This is the harness is Python. Python dependencies, right?
Yeah. Exactly. Like when this starts, it already has all the Python dependencies. They need to be staged before, and we have this basically a bootstrapping code here before that retrieves the dependencies we need, and then we start the container or the script or whatever we have. So executable stage is that the name is a bit odd, but really what it is, it's just a fused down version of all the operators. So we avoid creating too many processes. It would be very inefficient if for every ParDe we would have another container spun up. So we try to combine them in the same container. And so the executable stage is another operator now in Flink that again has to manage timers and state and multiple outputs and all the things we already have. But this time it's a little bit more complicated, because we communicate with an external process. We read data, we send them to the SDK, but also the SDK might come back and send state requests, timers, and so on. So this also all has to be taken into account. Also, watermark emission is slightly different if you have an async process which you're connected with, and you want to make sure that it actually received all the data. So we take care of this in the executable stage operator. One of the things which is interesting, maybe how it's modeled. For the state access, it's actually just calling out, sending a network request to the runner. For timers, we chose a little bit of a different approach. Timers are actually just elements of a special P collection. So whenever we set a timer, we output an element to basically ourselves, which we then receive, and we can set a timer inside the Flink, like the executable stage operator that receives all the input and sends everything to the SDK. And when then the timer fires, we actually emit again to a special P collection. So we have one for setting, one for firing, which is pretty interesting. It avoids to block every time when you set a timer, because you need to tell it to the runner, right? So we just emit it as part of a normal element. Yeah, I mentioned already AssignWindows is simply dropped because we are just assigning them directly in the SDK where we read our data. And finally, Impulse SDF, it's basically this new interface that I could probably, or that could probably be a talk about it on its own. Main difference is that you support dynamic splitting, which Flink does not really support, so it's a bit unclear how we implement it, but we have some ideas, at least until Flink does not support it natively. We have the idea to create basically a fixed hierarchy of like maybe a depth of 10 levels, and then we can do 10 times splitting, which is already really powerful, would be already really powerful. So that's due, but in the meantime, we can actually use cross-language transforms, which use the Java transforms inside Python pipelines, but I'm kind of running out of time, so I just keep it short and sweet. We have unit tests for all of this. We have also a suite called Validates Runner, which runs a lot of pipelines against the Flink Runner, both in the classic mode and the portable mode. And we have also special Python tests. For Python, there's also a compatibility matrix, which we update regularly. So for Flink, actually, it's pretty much everything is supported now, except the SDF supports billable doFn that I mentioned. So to conclude here, I hope you have learned that Beam and Flink are a great match. And Flink is really just a great framework to build your own data processing framework on top. And I think Beam has really, really compelling arguments to be used, since we have a unified API and we support multiple languages. So I think with Flink and Beam, you just have more possibilities, and that's always a great thing. So thank you for your attention, and I want to encourage you to check out the Portability website and subscribe to our mailing list, join the ASF Slack, follow Apache Beam or Beam Summit, which is a really cool conference about Apache Beam, and probably also attend maybe the next Beam Summit. Thank you.